I hope I'm not muted and then. So today I am going to cover something most important for computer science. As you know, this machine was discovered by Alan Turing or in 1936. And using this machine, he has shown that there are certain problems which cannot be solved. So basically, as you know, David Hilbert in 1900 asked these questions that while trying to prove something, can we have a systematic procedure, okay, to prove something? And that systematic or basically, mechanical means of proof. The mechanical word was misunderstood by Alan Turing, and that was the birth of computer science, right? Because the Turing machine turns out to be one of that mechanical means. So how can we compute certain things? People after this, and this is purely pen and paper computer, right? So it's a thought computer, I would say. And later on, people have come up with they try to make physical Turing machine, but that's another thing. There are many interesting challenges. Smallest Turing machine by this Wolfram. I'm sure, I don't know whether you heard about Stephen Wolfram. Have you heard? CP का आदमी नहीं है, but CP समझते हो ना, competitive programming का आदमी नहीं है. So at the age of 19, he finished his PhD, and he wanted to look at how the universe behave. So he wrote certain computer programs and try to simulate certain things based on the idea of cellular automata, which is also a part of computer science. I think I'm not going to cover here what is cellular automata, but very interesting thing. And he has written a very nice book, A New Kind of Science. It's a very thick book. It is available in the library. So you can see that everything in the universe, right from stock market to understanding of many natural processes, cellular automata is a very beautiful machine which can determines all kind of behavior. Okay, so so Wolfram has made a lot of money. He has this company Mathematica, that software that you might have seen. When you ask, if you have iPhone, if you ask Siri some typical mathematical questions, so that is answered by Wolfram, research engine, so it is answered by that, it is supported by Wolfram research engine. So that kind of person. I actually met him once. We took dinner together a long time ago. But anyway, so it's very interesting thing. So I'm going to talk about Turing machine first, and then briefly towards the end, I will also talk about linear bounded automata. I already discussed about finite state automata, push-down automata. Turing machine is left. Okay. So what is Turing machine? And why? First of all, why we should study Turing machine? As I mentioned earlier, I'm again reinforcing it, that whenever you discover any computational process in nature or in business or anywhere, I mean, you can actually map it to one of these four machines, And if we know that it is a Turing machine, so you can do wonders basically, because you know that with Turing machine, like this computer or laptop or your mobile phone, actually, they're all, one form of Turing machine only. The only thing is that in Turing machine, we have infinite tape, and here we have finite memory and everything is finite, so that is a key difference. Okay. So if you want to understand how in Facebook a new friend is joined, probably that network of Facebook or LinkedIn or any social media platform, it will be interesting to note that they follow certain chemistry. Those are purely, you can talk about entropy, enthalpy, and so on about the system, and actually they are computational process. Entire chemistry is a computer science. That one can show, one can show that entire chemistry is a computer science, right? So it's very important from that point of view. So Turing machine, so if you observe something, some process, for example, if I want to make computer out of bacteria, I want to show that bacteria can do Turing universal computation. By the way, you should know that bacteria have their own Facebook network, okay? And they send short messages to each other. And once there is a collection of bunch of short messages, they based on that they take collective decision to decide something about certain processes. Okay, so it's very important. Okay, so Turing machine is in that sense is very important. So for understanding nature actually, but as I mentioned, Turing machine also has a barrier. So there are certain problems that cannot be solved by Turing machine. So I'm going to throw some light on that also. Again, thanks to Professor Bush, right? So this is something I need to say all the time. So we have regular languages, context free. You saw that A and Bn cannot be accepted by any DFA or NFA, right? So we have these kind of languages, context free languages. Then there are languages like A and B and C and cannot be accepted by any push down automata. Push down automata with single stack memory, you cannot do that. You require at least push down automata with 2 stack memories, which is equivalent to Turing machine in some way. So these kind of languages cannot be accepted by single stack push down automata, right? So you require much more powerful machine, and that machine is nothing but a Turing machine. Okay. So what is Turing machine? Very simple concept. There is a tape, infinite tape, and there are certain cells inside, and there is a control unit. Control unit you can think of just like a DFA or NFA, whatever that. So like DFA is probably in the deterministic sense. So you have a start state and bunch of final states, right? And you're moving between, right? Control unit and a tape. And you require a head, read-write head, which can read or write. So first of all, note that tape has no boundaries, infinite length, and the head moves either left or right. Okay, can move left or right. What head can do? The head at each transition, time step, reads a symbol in the tape, writes a symbol, read something, write something, and move either left or right. These are the 3 possibilities for the head of the Turing machine. So for example, here we are reading A and writing B, right? So basically, sorry, writing K, reading A here, writing K and moving left, moves left, right? That's what we are doing here. You can see that, right? Reading A, this pointer means we are reading that symbol. Then we replace basically A with K, okay, and then move left. Okay, this is one typical scenario. Another one, read read B and write F and move right. I hope it is clear, right? What is happening? So on the tape, input is given on the tape, and before the input and after the input, there are certain blank symbols. This is something new concept. Put blank symbols, this kind of symbol, okay? This diamond shaped symbol is blank symbol. So head starts at the leftmost position of the input string from here. We will start the computation from here. This is the input, initial input, right? We start the computation from here. Now, what are the states and transitions? We are in some state Q1, okay? Read A, write B, and move towards left and change state to Q2 from Q1. Okay, this is a typical scenario. Similarly, here, read A, write B, move towards right and change state from Q1 to Q2. Okay, these are the typical transitions and the state relationship. Okay. So for example, what does that mean? You're reading A, write B, so A will become B and move towards right, and the state changes from Q1 to Q2. So you move towards right. So A will become B and you move towards right. And new state is written here, Q2. Got it? Simple calculations. This one? Yeah, so read A, write B. You just read this line. Read A, it's reading A, write B, and move towards right. Okay? Similarly, what about this? Read A, write B, move towards left, state changes from Q1 to Q2. Right? It's very clear. What about this? Read blank symbol. Read blank symbol. Right? Write G and move towards right. Again, blank symbol. Right? I hope just look at the line, last line, and then you get the picture. It will be clear to you. Right? What is happening? Now, Turing machines, what we are going to focus are deterministic Turing machines. Means for one input, there is only one deterministic choice to go. Okay. I am not allowing, these kind of things are not allowed. For one symbol, we have two transitions. This is not allowed. Okay. They are deterministic in nature. This is a possibility for different symbols. We are going to different places, right? That is okay. And no lambda transitions. Okay. There are a couple of more assumptions which I am going to tell you. Partial transition function is allowed. It may happen with no transition for input symbol C, for example, you see. So this is a machine. For A, I know what to do. For B, if you receive B, I know what to do. But if you receive C, I am not telling you what to do. This is a possibility in Turing machine. So no transition for some symbols. So the transition function is partial transition function, right? It's not completely mapping for each input. We are not worrying about for each input. Many times, actually does not scan anything and also accepts the string. That is also a possibility. I will tell you about those things later on. Halting. The machine halts in a state if there is no transition to follow. Okay? A machine halts in a state if there is no transition to follow. For example, this is halting example 1. I'm not telling you what to do if you are in state Q1, right? So machine will halt. Right? Machine is in Q1, right? Reading symbol C. It will halt. Okay? This is one example of halting. Another halting example. So this is the machine. I mean the control unit of the machine. You can see that for A and B, I am telling you what to do. But now machine is reading symbol C, and there is no possible transition from Q1 and symbol C, right? So machine will halt. That's another example of halting. Okay. So there are different versions of halting. Another thing is this. This is allowed. So incoming transitions are allowed in the accepting state, but no outgoing. So accepting states have no outgoing transitions. Okay. So basically, this is not allowed. Accepting state should not have a outgoing transition. Okay. This is another assumption. Okay. So that means once machine halts, it's accept, Okay. So how do we accept? Accept the input string if machine halts in an accepting state. Machine halt. I showed you a bunch of examples of halting, right? Machine halts in the accepting state. So you accept, right? Reject input string if machine halts in a non-accepting state, or it may happen machine enters into an infinite loop. While doing programming, you might have encountered these things, right? Sometime if you have done enough programming, right? So I need to assume that then you might have experienced these things, Machine enters infinite loop. Observation, this is a very important observation. In order to accept an input string, it is not necessary to scan all the symbols in the string. You saw that for symbol C, we have no way to go, right? So this may be possibility, right? In order to accept any input string, it is not necessary to scan all the symbols in the string. Okay, this is something important. Now let us look at some examples. This is a very simple example. Alphabet is A, B. And this machine accepts the language A star. A star means all possibilities of A, right? So Suppose the string is A. What will happen? You read A, keep moving right until you hit the blank symbol, right? You replace blank symbol with blank symbol actually and move towards left and stop, right? That's what will happen. So let me show you. So A, you read A, move right. You read A, move right. You read A, move right. You hit a blank symbol, right? Move left and stop at A, the last one. Halt and stop, accept, right? So A is accepted. So now you can see that here, we started when the head was here, right? And we ended when the head is here. Sometime you will see that we also stop the machine and we move the head towards the first one where it is started. That is also a possibility. I'll show you some examples, right? So that is a possibility, right? So normally what we say, when we finish the thing, we stop, and here we are making it to stop, the last symbol, okay? Rejection example, if the string is ABA, so what will happen? Read A, move right, read B. I mean, there is no possible transition. The machine will halt as per the definition, and so it rejects. It's not in accepting state, right? This string ABA will be rejected. This is a very simple. If the alphabet is only sigma is equal to singleton A, this is also a machine, Turing machine. Just simply, it will halt and accept. So AAA will be accepted, not necessary to scan the input. That condition, as I mentioned, right? Not necessary to scan the input, you accept. Now, this example, you see it's the infinite loop example. So I think by now you know what is regular expression. So these, you know, right? So let me see. So in this machine, you will see that it's kind of, I'll show you with some small example string. ABA. So what will happen? You read A, move towards right. You read B, move towards left. You read A, move towards right, like that. Keep on doing, right? Infinite loop, right? This is a possibility. Kind of infinite loop. Aage piche, right? That is. So because of the infinite loop, the accepting state cannot be reached. The machine never halts. The input string is rejected. Okay. So I think that's also another important thing to observe. Now, our first example, first non-trivial example, A and Bn. We saw A and Bn can be accepted by push-down automata, right? With the help of a stack. You keep on matching with, right? You push A, right? Push A, and then pop B, same number of times, right? That's was here. This machine is going to solve the problem. By the way, one thing I should tell you in this automata business, it may happen that you may design a DFA or NFA which will have a different answer than some other person. Answers may be different, right? Because how do you think about it, right? Same thing with Turing machines. Somebody may have 10 states, somebody will have 10 states, 15 states. All this is possible. So don't compare your answers. No, my answer is. Of course, you can say that which one is the best one. Something which requires less resources, minimum number of states is obviously a good thing, right? Okay, so that may be a possibility. So now, so somebody has created this machine to accept A and Bn. You may have a different answer. You have to think about it, how to create. So let me give you the key idea how we accept A and Bn. Okay. So how do we start? What we are going to do? So remember in the stack business PDA, what we have done? We push A, and then pop B. That matching was done. Here also we have to do somehow this matching. Now here, how we'll do matching? I will replace A with X, next A with X, next A with X. Okay, and then we'll go to the next B and replace B with Y, B with Y, B with Y. These kind of things we will do. Okay, so that's how matching can be done. So let me show you. So match A and B. This is the basic idea. Replace leftmost A with X. Because I have written leftmost A, so whenever I do replacement, I'll go back and do the. So suppose I replace A with X. Then I go, so the string is A, B, B, B. So first A I will replace with X. I go to the next, B and replace it with Y. I come back here and replace the second A with X. I go and there, and the second B is replaced with Y, and like that we continue. Okay, that is how it moves. So replace leftmost A with X, find leftmost B and replace it with Y until there are no more A's and B's. If there is a remaining A or B, reject. Right? That means they are not matching. Right? This is how we can do the matching business here. So let me show you with a small example. A, B, B. So what you do? The first machine, replace A with X, move right. Then what? You see, now I am going to read next A. I have to skip this. So that's why this is there. Just move, read next A and move right. I'm not worrying about the next A at the moment, right? So move towards right. I read first B. Now first B, then I replace it with Y. Right? Replace it with Y and then move left, back. Then I read first A. Again, you go back. Here you can modify the machine if you want, right? I mean, it's up to you. Anyway, how do we play with the things? But here what we are doing, we are coming back, reading X, okay, move right, then reading A, next A, move, replace it with X, read Y, we are moving again, read next B, right? Next B is replaced with Y. Now we are done. Matching is done. But we want to stop it somewhere. So I'll come back, I will come back, and I'm stopping it here actually. Read this. Once you read the blank symbol, you move the head towards the last symbol, which is Y, halt and accept. Okay, little bit non-trivial, but it's beautiful, right? I mean, you can see how to design these things, right? So your answer may be different, how you're doing the calculations, it matters a lot. Okay, how you do the calculations, that matters a lot. So what you require, please do some practice, because assignment 4 is on, I have given you 2 problems on Turing machines. One for finding subtraction of 2 numbers. I will show you an example of addition of 2 numbers. Similar idea works for subtraction. I mean, you can have your own idea perfectly fine, no problem. Okay, and then also you can find maxima, minima, whatever you want. Division. Can you do division with Turing machine? Division of 2 numbers, whatever arithmetic you want to do. How to find a square root? Basic things, right? So I'm telling you the questions, right? What can be asked? So that is, so maybe. So T problem, you modify this machine to accept A and B and Cn. You have to do some more modifications, right? To accept this language, A and B and Cn. Okay, that is your first practice. So you know how to accept A and B and that machine I have given to you. You have to design a machine for accepting the language A and B and Cn, right? Some modification you need to do. You have to take care of C and replace it with Z, right? Those kind of things you have to do. Okay, so this was background material. Now I'm ready to give you formal definition of Turing machine, and then I'll talk about the language. Just like IDs we have in pushdown automata, we have instant, IDs, one ID, another ID, another ID, starting from initial state and going to the final state of IDs. You collect all of them there, so you can do that, and then so that can form the language. That gives you motivation for language. Same thing here for the Turing machines. Once we will do that, then I will talk about how to compute certain functions with the Turing machine. So transition function. So this thing, what I have written is, in pictures, can be written as you are in state Q1. After reading A, you go to state Q2, replace A with B, basically, and move towards right. Okay, that's what you can do. Similarly, this one, delta Q1C is equal to Q2 comma D comma L, right? Replace A, C with D and move towards left. The state changes from Q1 to Q2. These are the typical examples. So Turing machine is a 7-tuple Q set of states, sigma input alphabet, gamma tape alphabet, delta is a transition function, Q naught is the initial state. Blank symbols are also required on the around the input side, and F set of accepting states, right? This is a typical scenario, and with the help of, so basically your first program. So if I ask you, write a computer program for adding two numbers by a Turing machine, so what you need? You need a transition table, right? Once you have the transition table, you know that is the actual programming for this Turing machine. Now we can talk about the language. So configuration, this typical scenario can be written like CA is the initial thing. Q1, head is reading B. Head is reading B, so we place Q1 here and BA, right? So this is a typical ID, instantaneous description of the Turing machine at a given time, right? So that means there could be multiple of them. We can move from here to there. That is in pictures. That is in symbols. So in general, we can say that a bigger computation can be different moves, certain number of moves from start state to final state, right? So all this can be written as from this in 0 or more operations, we arrive at this 0 or more moves. Okay. So initial configuration Q naught W. When we write Q naught W, so it is reading Q naught is we make an arrow to A, and AABB is the input string. So that is W. This is the initial configuration. Okay. So the accepted languages for any Turing machine M, all those strings W such that from initial configuration in 0 or more move, we go to the final configuration. That's all. Okay. Yes. 0 or more means it could be 0, it could be 1, it could be 2, any number. I don't care. I mean, this is what I'm saying, that this is the way it is set as 0. So sometimes what it happens, it is not moving at all actually. The configuration doesn't change. As you saw in one example, not necessary to scan any input and you accept. That is also a possibility, right? There could be only one ID. So when the initial and final will coincide, basically, right? Okay, so if a language is accepted by a Turing machine, then we say that L is Turing recognizable. Other names are Turing acceptable or recursively enumerable languages. This is another word used for it. Okay, so now we are ready with computing functions with Turing machines. Okay, how to compute functions? It's very easy. So the function is what? A rule associated with every element in a domain, giving unique image in the codomain, and range is a subset of codomain anyway. So now, if this is a domain, this is a result. This is a function. So, and function may have several parameters. For example, this addition function has 2 parameters, x comma y. Fxy is equal to x plus y, right? So we do unary encoding here. Unary encoding is very, very important. It's easy to handle the stuff, So basically, this is decimal, this is binary. Unary means everything is number of ones. So if I have to add 5 and 3, 5 will be 1, 1, 1, 1, 1, and 3 will be 1, 1, 1. So we can design a machine which will add these two things. Okay, it's easy for us. So we prefer unary representation. A function f is computable if there is a Turing machine M such that with initial configuration like this, we go to the final configuration f of w. So w is here as an input, f of w is as an output on the tape. Then we say that this function can be computed by the Turing machine. Okay, we can compute the function. Initial configuration gives you final configuration. So initial configuration is w, final configuration is f of w. Okay, for all w in D. So in other words, a function is computable if there is a Turing machine M such that with initial configuration Q0W, we can go to the final configuration QF f of W, final configuration for all W in D. Okay, so let me show you the example for addition. So fxy, so we say that the function is computable. Okay, here we are very simple things. We are assuming x and y are integers. So input string is something like this. 0 0 is a delimiter. You know, I can put any other symbols if I want. X, 0, Y. And final output is X, Y together and 0 at the last. So I have to design functions in such a manner, starting from X, 0, Y. X and Y we want to add. So X number of ones are there. 0, Y number of ones are there. And then we addition, so the final configuration, X plus Y number of ones are there, followed by 0 at the last, right? We have to design functions which can do these things. So this is a typical scenario. So we have X number of ones, 0, Y number of ones, and blank symbols. So 0 separates that two integers. This is the initial state. Final state, X plus Y number of ones, final 0, right? And Q of is reading the final state, right? So the question is, how do we design Turing machine which can add these two numbers? Any idea? So we have ones. So basically, if we have somehow we have to change the delimiter in between, right? Right? So 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, right? So let me show you the example. Here is the Turing machine for addition. So what we are doing, starting from the first symbol 1, right? Keep reading, keep reading, keep reading. If X number of ones are there, we'll read. Once we hit first 0, we replace that 0 with 1, move towards right, keep reading, keep reading, keep reading for 1. Then you hit the blank symbol, right? Once you hit the blank symbol, you move left, replace last one with 0. Last one with 0, because we have middle 0, we have replaced with 1. So there is one extra 1, right? So the last one I'll make 0, right? And then we'll come back, you know, come back and then we'll stop wherever I want to stop. So that's, you know, I'll show you. So if X is 1, 1, Y is 1, 1, this is the initial thing. Okay. And final result is 1, 1, 1, 1. So what we do? Read 1, move right. Read 1, move right. Read 0, replace it with 1, move right. Read 1, move right. Read 1, move right. Hit blank symbol, move left. Replace last one with 0. Keep moving left, 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 left. We hit blank symbol. We move it to the first. We are stopping at the first position and accepting. Got it? Remember, in the one example I have shown you toward the last symbol I am stopping. Here I am stopping at the first symbol, right? It's up to in our hand, you know, what we do want to do actually. How do we actually दिमाग का खेल है और कुछ नहीं, right? How do we do calculations, right? That's all. So this is addition of two numbers. Similarly, you can compute f of x equal to 2x. So input should be x, output should be x. So, you know, it's a special case of addition anyway. Initial state, final state. I'm skipping this so you can make the Turing machine at your t time. When the function is something like this, f of x y is equal to 1 if x is greater than y and 0 if x is less than or equal to y. So input is x, delimiter y, output is either 1 or 0. You see the function. How do we compute this kind of function with the Turing machine? So now, actually, what we do, pseudocode is there, match a1 from x with a 1 from y, 1 from a, so 1 from x and 1 from y, because there are certain number of ones and certain number of, so x number of ones and say y number of ones are also there, right? Separate. Which one is bigger? If x is bigger, either three possibilities, either x is greater than y, or x is less than y, or x is equal to y, right? Three possibilities. So until all of x and y is matched, if a 1 from x is not matched, erase tape, write 1, that means x is greater than 1. Else erase tape, write 0, x is less than or equal to y. So this is a pseudocode, and here is a machine. You know, so basically that is how you can do. So I think you can combine. So basically, you can combine two Turing machines. I should show you how do you combine. So you can have a machine for comparing, you can have a machine for adder, you can have a machine for eraser, and that will compute this function. So this combination is sometimes easy. Take one machine for doing certain things, another machine for doing some certain things, another machine for doing certain things. But I think this is, combination will be a little bit initially harder, but so I think that's okay if you don't understand much. Okay, so I think that's all about computation of numbers. Now, these Turing machines, I showed you single tape. For certain complicated problems, it might be difficult to come up with a Turing machine with single tape. So there are certain variations of the Turing machines. I will briefly give you an overview of variations of Turing machines, what are possible. And sometimes those Turing machines are easy to handle. Okay. So rather than going over any proof, I'm not going to show you any proof, but only I will show you some pictures. Pictures you watch anyway, right? Okay, again, thank you to Professor Bush. So we can start. Skip all this. So a standard model is infinite tape, some input is there, read write head is there, which can move left or right, and control unit, which is deterministic, right? This is a standard model of Turing machine. I can have a stay option machine. A stay option machine, head can move left or right, or it can stay at the same position. The possibility. So if you do this variation, the computational power of this machine is same thing as the standard Turing machine, but it is easy to handle more complex problems, while designing. So here is, so these are the stay options, semi-infinite, offline, multi-tape, multi-dimensional, non-deterministic. All will give you same power. One can show all are same. I am not going to prove anything. I will just show you the definitions of each of these cases. That's all, which is not very difficult to look at. ये सब बकवास है अभी, right? So Turing machine with stay option. So head can move left, right, or stay. Okay, stay is there. You see, from time 1, reading A, replace it with B, and stay at the same place. Stay at the same place, right? Reading A, replace it with B, and stay at the same place. State changes to Q2. Stay option machine, right? This is a possibility. One thing, stay option can be implemented with a standard Turing machine. You move left and move right. You will come back to the same place. That is a possibility, right? बाकी ये सब छोड़ दो, हाँ ये आगे. Multiple track. So we have multi-track. So track 1, track 2, track 3. So this combined symbol of here and here is just one symbol, A comma B, and one head is reading 2 things at a time, or 3 things at a time, or 4 things at a time. Okay, this is multiple track. These things are quite useful when we solve complicated problems with Turing machines. Okay, in terms of power, they are same as a standard Turing machine. So fine, I think this is, you see the typical, typical transition is something like this, right? Semi-infinite tape. So on one side, it is blocked. Infinite on one direction only. So basically, you have to implement like you come up to this point, and once you come here, you stay here or go on the right. If you implement like that, So when it moves left from the border, it remains at the same place. You can implement like that. Semi-infinite tape. बस ये सब छोड़ दो. Offline machine. So input you can read only once, control unit, and then on the tape you can do the read and write, right? So input appears on the input file only once, so read only once. Offline machine is there. Fine, we leave this. Multi-tape Turing machine. Tape 1, tape 2. That was multi-track. Single tape, multiple tracks. There are multiple tapes. Tape 1, tape 2, tape 3. And then, control is working on all of them. Yeah, how head will work, you see? Here is the head. Right? So here you see in tape 1, you read B. So tape 1, you do this. Tape 2, you do this. Tape 3, you do something else. That's okay. Okay. So again, this is all useless at this moment. By the way, same power does not apply same speed. So this, for example, certain things can be done in order of n square. You don't know what is order of n square. I'm going to talk about it later on. Big O notation, beautiful notation. I love this stuff. So you might have, वो data structure में कर रहे होगे, right? Who invented big O notation? No. There is a very famous book. अगर नहीं पढ़ी तो मजा नहीं आया है. G.H. Hardy की Order of Infinity book पढ़ो. That talks about these things only. Beautiful book. Anyway, so something can be done in faster time actually. All these machines, time could be better, but the computing power is same. ये भी हो गया. हाँ, multi-dimensional Turing machine. So two-dimensional tape. Head can move left, right, up, down. Okay, that is also a possibility. You can define multi-dimensional Turing machine. This is two-dimensional. You can define three-dimensional Turing machine, five-dimensional Turing machine, k-dimensional Turing machine. I hope you can visualize how difficult it will be to do the things, but non-deterministic Turing machine. So for one input you have multiple choices. That means the same thing in parallel computations will go on, right? That kind of stuff. And I think that's all done. So now, so we have covered about the Turing machine. अभी घर जाके करना क्या है? चाय का कप लेकर के थोड़ी ट्यूरिंग मशीन की प्रॉब्लम्स कर लेना, राइट? एडिशन तो हमने दिखा दिया है, सब्ट्रैक्शन का एग्जांपल दिया है, मैक्सिमा मिनिमा कैसे फाइंड आउट करेंगे, और कपल ऑफ अदर अरिथमेटिक ऑपरेशंस, हाउ यू विल डू इट. जस्ट डू कपल ऑफ एग्जांपल्स. One can ask interesting questions. Design a Turing machine for adding two numbers with minimum number of states, or with the minimum number of all kind of questions. You can optimize these things, but that is something interesting thing. Now, last thing probably for today. अभी तो बहुत टाइम है एक्चुअली ना. Okay, so this is the final Chomsky hierarchy. What is Chomsky hierarchy? As you know, Noam Chomsky, who was a linguist, gave this classification of that slide which I showed to you earlier. Now we can talk about what is linear bounded automata. Same thing as a Turing machine with one difference. The input string tape space is the only tape space allowed to use. So basically, you can only work here to here. You cannot go outside. That's a linear bounded automata. A special kind of Turing machine, right? You are allowed to use the space, whatever is the input size. Okay, so that is also very interesting thing. Although people do not study much about it, but so I think you can also skip. There are many interesting problems. I can skip right now. Unrestricted grammar. So I can talk about now. I can classify these four machines with the help of grammar. Four different grammars will give you four different languages. All those four languages can be accepted by different machines, right? Four machines. So when the production rules are U going to V, U is a string of variables and terminals, V is a string of variables and terminals. There is no restriction on either side. Unrestricted grammar generates recursively enumerable languages accepted by Turing machine. Okay? This is the most powerful model. Then this is the example of unrestricted grammar. Either side, any combination. So a language L is Turing acceptable if and only if it is rated by unrestricted grammar. No need to study proof anything at this moment. Context sensitive grammar. If production rules are like this, a string of variables and terminals, a string of variables and terminals, and size of U is less than or equal to size of V. Linear bounded automata machine. Okay, we are putting restrictions. Okay, so this is the LBA. Context sensitive grammar. Context sensitive. So this is an example of context sensitive, accepted by LBA, linear bounded automata. And I think I already talked about other two grammars: context free grammar and regular grammar. तो काफी कुछ खत्म हो गया. Now we are left with one thing, like something very fundamental, that there are many problems which you cannot solve. Each one have a different capacity, right? That boy sitting there may be having different capacity of solving problems. You might be having different capacity. Similarly, Turing machine has a different capacity. So one can show that there are more languages than the number of Turing machines. So there are certain languages for which we cannot construct any Turing machine. Okay, this is the SAR, basically the whole thing. So I can give you a proof if you want. आज नहीं तो कल की नेक्स्ट क्लास में थोड़ा सा बात कर सकते हैं इसके बारे में. And I think that's all. Fair. I think you have exam also, right? I hope you are studying. I think, by the way, yeah, पूछो. Context sensitive, yeah. So context sensitive when the size is less, right? Size of U is less than or equal to size of V. You are asking for the exam? Okay. Whether it is in the exam or not. So exam में तो last class तक सब कुछ है. That is how the system is, right? So अभी you need to focus on Turing machine business little bit more and then PDA and all these things. मजा आएगा एग्जाम में, राइट? एंजॉय करोगे. Basically, what we know, we have some time. Should we do something more? Okay, so see you in the next class. Enjoy karo. Good luck. By the way, all these slides are available in that lecture folder. If you have not accessed it, you can access it, right? All the slides are there.